Welcome to our talk. Thanks for coming. This is called Happy Paths, Functional Constructs in the Wild. I'm James Kionka.
And I'm Joe Walp.
And we are software engineers at PayPal, where we are actively using Scala in production code. So, of course, although we work for PayPal, this has nothing to do with PayPal. These statements and opinions are purely our own. Part of the reason I wanted to give this talk is people have accused me of having hate-oriented programming or something along those lines. But that's not true. I just have pessimism. And that's like really the only responsible way to program, I feel. You have to verify. There's no trust but verify. It's always verify. And the purpose of this talk in particular will be comparing how Scala and Scala-Z accomplish various functional tasks in Scala, especially focusing around monads. And we will get into those and give hopefully a easier explanation than maybe you've seen before. There have been many libraries produced. Scala-Z is, of course, the most famous, but also Cats, Scholastic, and Structures. They all provide this category theoretic approach. And Scala's is, a lot more explicit. It's just assumed that if you implemented flatMap and map, things are going to turn out okay. And we're going to see how to use these features in our code base, and we're going to be motivating them through interactions that you'll have with Java, because you will certainly have those interactions. And in particular, we're going to try and focus on how we can accomplish that using mostly the standard library. And our first choice will be taking a look at option, which I assume everyone is very, very familiar with. This is just a very basic example of how you would use it. You can have it as sum or none. That's all good. And in particular, we're particularly worried in Scala about dealing with nulls. So many, or maybe most, Java methods will return a null, and we want to have a type-safe way of dealing with this. In fact, we want the type system to force us to deal with this, and we're going to expand on this idea. Of course, you have to use them correctly. Have you ever seen a null in a sum? Because you can totally do that, and that should really, really bother you. It scares me. So the point is, just don't ever use the sum constructor. Just don't do it. And the null pointer exception is really the most thrown exception in the JVM. So I think this is a very relevant case, even though it's very basic, and it will help us motivate some other monads in the future. When we're working with options, you can use pattern matching to get at it. This is an intermediate talk, but I'm not sure what level really to go at. You can also use them in these 4 yield comprehensions. And this is perhaps the most common way you'll see them. And you can also map over them. That's just assuming that you have a sum type. If it's a none, this just evaluates to a none. So I'm just going on quickly. I'm sure this is all very known to you. Assuming we have some case classes that I like to work with, and
slow down a little.
Yeah. So it's very often the case that you'll have functions that return option, even if it's not a null. Oftentimes there's just not information there. It needs to be represented as such. But it's also somewhat limiting, right? Like, you don't know why it failed. You just know something failed, something's missing. So it's a little bit limited, but it's common enough that you still see it in code all the time. Since this is the simplest monad you commonly see, we're going to compare that to what Scala-Z provides. And they have maybe, which is invariant, while option is covariant. and it does not expose an unsafe Git. Otherwise, these things are very similar. In fact, you don't really gain that much from using this. They're just really, really determined that you have the best environment to work out of. For example, in cats, they actually just use the option. They don't bother having a maybe. And we're going to get to what the difference between the invariance and covariance means a little bit later. Also, you can't use the maybe constructor. You have to use this, and that was actually added later. So now we've quickly gone over the fact that you can put a context around a type and say it may or may not be there. Expanding on this idea, the other thing that you see constantly while working with Java APIs are exceptions. Sometimes it's even within the regular flow. So Scala has provided a what we're going to call a monad, which is try. This is just simple, trivial use cases. If you use a try constructor, it'll catch most exceptions. Actually, all exception types and a little bit more. We'll talk about that in a second. You can use the raw constructors very similarly to how they were used in option. However, also like you use with option, if you ever wrap a success around something that you were just positive was going to be a success and it throws, it will just throw out of it. It's not maybe as safe as you might assume. And here actually is one of my favorite examples from this. If you want to deal with calls to Java in a very functional way, then this is actually the simplest and safest way to do it, because surely it will give you a null and it'll probably throw in the process too. So you're already 2 levels deep here, and many times you will have tries of options and you have to extract them and deal with them. Perhaps you feel like you might want to reach for something that will deal with this better. That's monad transformers when you have them stacked like that. But we're not going to get too deep into that. But I just really like this example because that's as simple as it's going to get.
And then one more layer would be a list of tries of options.
Yeah. And that will exist in your code base, especially when you try and encapsulate as many of these conditions into your types as possible. And because you put them in the type system forces you to deal with them rationally, unlike how you would probably deal with them. And again, the similarity between option and try is very large. It's very similar, except you have a failure case here instead of a none, and that contains a throwable. So now you can actually know why it failed. It's actually a much more useful representation usually. Even if something gave you an option back, you might almost immediately move it into a try, just so you know this is why this is no good. Very similarly, you can also map over it, assuming it's a success. Otherwise, you still have your failure. And this is
one more comment about tries. It's really easy to incrementally migrate your code base to using tries. So what you can do is go ahead and transform the method that you happen to be touching for the piece of maintenance programming that you happen to be performing. And then at the bottom you can call get on that try, and it'll throw the regular exception that you would have thrown regardless, so that your consumer code can when you're ready to migrate the consumer code for this method, you can just get rid of that .get at the end.
Yeah, that's actually a really good point, because moving to tries will help you move to a more functional code base, and you can continue refactorings on from there, as we will compare with the Scala Z equivalents. Something else I really wanted to talk about with tries, they actually don't catch just exceptions. And the failure type would maybe lead you to believe that they actually catch throwables. Neither of those things is true. It actually only catches non-fatal exceptions. So you might be wondering what those are. Scala defines them for you. This is the list of them, in fact. And you know, one of the other things I really don't like about non-fatal is that it starts with non. Like, of course, like it's confusing when you refer to it. You're going to have double negatives very frequently in your code base, which is a danger. And this is also, list has changed over time. For example, not implemented error was made non-fatal in 2003, and Stack Overflow exception was made fatal. So, you know, it's not necessarily hard-coded, and it's something you really, I think, want to keep in mind when dealing with tries and exceptions in general.
Yeah, it comes up when you want to provide logging around this particular class of exception.
Yeah, so I wish that there had been a way to do a more specific type, but this is probably what was done best for compatibility. So Scala Z actually doesn't give you a regular construct like try to deal with your exceptions. They actually would rather that you put them into their either type, and they refer to it as disjunction and either interchangeably, but the issue is obviously the Scala either gets confusing with that. So disjunction is more popular, and that's actually not a V, unfortunately. That's is a backward slash and a forward slash. So if you're not used to seeing that, that is a valid Scala syntax. You can always put a constructor, a type constructor, in the middle if it has two type parameters. So this is just an example of how you can catch non-fatal exceptions, and it stores it as a throwable as well, you know, similarly to how failure works. But what's nice about it is that it actually gives you the explicit exception types. You know, you can just use non-fatal, or if you use this from try catch throwable, you can actually specify the type of exceptions you would like to catch. And if it's not that type, then it won't catch them. It's a pretty nifty trick. The only really confusing thing here is they switched the type parameters from that to disjunction, which is pretty confusing. But it gives you a lot of flexibility, and it allows you to really specify the type of exception that you would have normally, which you can't do with tries. And I should have made this not go down so far. But you can also catch throwables even, you know, if you specify that. Or in this case, you know, I specified exception and a throwable escaped. So that's the nice ability that they have with disjunction. And so why not just use either? Or why not use try? Well, the either in Scala, as you probably know, is not biased to the left or the right side. So flat mapping and mapping over it is not as convenient as you'd like. You could override those and define them on it, which I believe is the way that CATS has approached it so far. Their primary reason against try is it's not expressive enough. And I'd also just like to give a shout out to CATS documentation. It's not complete by any means, but if you're into category theory, it's pretty impressive introduction, and it's getting better. You'll still have to go to other sources, but I found it useful.
But the point here is you have a code base. It is interacting with Java. You do need to wrap up all those exceptions that the Java API is giving you. And you have a couple, actually several paths that you can choose from. Like CATS is something on the bleeding edge. If you stay within the standard library, try is pretty usable. It's really nice if you want to publish something for public consumption, an open source project. That way you're not creating a dependency on Scala Z, which may or not be acceptable in a given organization. And then you have the other path that's more pure. tries to express things in as monadic a form as possible. And your options there are, again, cats or Scala Z, which is more mature but has its flavor of syntax that is not acceptable to a lot of programmers. This mixture of symbolic names can be a real gobbledygook for maintenance within a larger organization. So just to kind of give a global overview in each case, we're showing you that you, as a programmer, you have this conceptual path where you're trying to become more and more familiar with the monadic constructs, and there's a clear progression there from Java land and object-oriented programming to the standard library to the more monadic forms that you find in a library that expresses those monadic forms in the hierarchy. But when it comes to evolving a code base, it's not a linear progression. It really is you are choosing a path, right? You're choosing the standard library path, or alternately the more pure form, because they're not they don't play nicely together, and they do have different maintenance characteristics and employee education characteristics.
Yes, that's a good point. And also, Cats is not production ready yet. It's actually very much under development. But I still, that's the logo for it. I thought it's really cute category. So take a step back here for a second. We have these types which hold a type. And why that's really exciting is because it encapsulates some truth about it that we need to force ourselves to deal with. The term for this is that you have a kind from star to star. A regular type is just a kind star, and if you actually fill in that type, then it breaks down just to a kind star as well. Just a little bit of useful terminology if you might be looking into some of the more category theory type libraries. And so in the previous slides, I showed you that you were able to map over these things, and you may not have thought anything special about that. But from category theory, a map actually has very specific rules on how it can map over whatever is in this context, whatever is in this monad. In particular, this functor, which is just a weaker form, or a more general form of a monad. And we have these simple rules that we need to deal with. If you map over the identity, you should get the same thing back. If you do two maps, that should be the same as if you did one map and then the next within the same map. So what can we generally get out of those meanings? It means you can't change the internal structure of a functor, right? If you have a list and you're mapping over it, you would not expect to get a different number of elements back, right? Or you wouldn't expect any kind of side effect or magic to happen. This is actually one of the key arguments why people think that set is not a functor. It's something of a disagreement. It has to do with the fact that equality is not really defined in the functor definition, and you can collapse the internal structure of the set, at which point you're changing the structure and you don't get to define equality. So it's actually a dangerous concept and not technically permitted. And so I mentioned this. So a functor is just a context, it's a type that has a map on it. Similarly, monads are a very special type of functor that define flatMap and pure as well. Pure is inherited from, these are just the necessary things. I didn't actually list the laws here. We're getting to that. So as you can see, we've had this structure where we have used flatMap, or this for yield structure, to get whatever is inside this context and then use it in the future in further computations. This is actually directly equivalent to this larger, written out form, and the yield is actually a map, it's not a flat map, which is not necessary, but it's just the way that Scala has implemented it. They seem to think that you might want to map at the end. So I just want to show you that this flat map is equivalent from this definition where we're using it. It seems pretty abstract right here. Okay, so I tried to give some intuition about the functor laws before. These are harder. But if you squint and you just try and imagine like monads as containers, which are popular, or boxes, you know, you would feel like it would be wrong if you were to just put something into a box, map or apply this function to it, then put it in another box. You would assume that these things could happen without any danger. Similarly, if you had something already in the box and then you put it in a nice clean box, you would assume that hopefully it's the same idea. And if you applied them in different orders, you know, it's just the how you would assume that you can safely work with them. If they didn't follow these laws, then it'd be very difficult to reason about. Okay, so I hope that made the functor and monad laws a little bit less scary, a little bit less abstract than just something someone told you that you had to follow. Now we're going to look a little bit closer at how to deal with lists of monads, which is what you will run into constantly. Once you start trying to model options and tries everywhere, pretty soon you have lists, and that's what we have right here. We have a function which takes a name, returns a try of a person, and then we map over this list of names and we get a list of try of person. But that's not really what we wanted. It's a very difficult type to work with. We prefer it to be a try of list. We just want to know like what went wrong. So Scala Z and other category theory libraries provide sequence to do this. And what it does is if you take a list and some monad, you can always switch the types. It's kind of like magic. Yeah, perhaps it would be best if you could use that.
Yeah, sorry. This does not appear to preserve the semantics, though. I mean, there needs to be some sort of aggregation of failures, because if you have a list of tries, then you may have a number of failures, whereas with a try, you only get one.
That's right.
Yeah, so it's not the same.
Yes, that's true. So yes, as you pointed out, there are a list of tries. Many of them could be failures, but sequence will actually only return you the first failure. This is actually kind of similar to how it would happen in a Java program. If you tried running each one of these, once one of them throws the exception, you really just get that first one. They are different, but compared to the Java throwing, it's somewhat similar. And is often sufficient in our use cases. Maybe if you were more concerned, you could collect all of the failure cases and present them. So the point being is that when you have nested monads, you often, or yes, nested types, you often have a lot of explicit data, and it can be difficult to process these things, as Wadler said. So here's a little bit of a similar example that I've taken from our code base through modifications. So we want a try of an option of a list of columns from the database. We get a result, well, we put it in a row that we got from earlier, perhaps in a four-yield try comprehension. And then we map over it to validate that the columns are good, but then we need to sequence them back, and then we have an option of try uplist, and that's very close to what we want. We actually wanted a try on the outside, so we sequenced them again. And now we're able to have this pleasant type to work with. We can continue using it in the four-yield comprehension of tries.
And for what it's worth, this is code very similar to what we have in our code base.
Yeah, so maybe we're doing it wrong, you know. But I feel like this is a reasonable approach to take. And so, of course, you know, how did this dot sequence just magically appear on your types? It doesn't magically appear. We actually need to define it on basically every combination that you might encounter. For our use cases, mostly it's just list and try. We have a few other cases. This is actually open source software in Cascade now, so if you actually find yourself in a very similar situation and you're not allowed to use Scala Z or something like that, then you know these are good workarounds. I only put these up here as examples. You don't actually have to read this code. And this is an example from Scala Z. It's defined in a traverse, in the first trait. And F has to be a functor and foldable in this case, but just read it as list. And G has to be applicative, which is just a more general form of a monad. So if you have a monad, that's perfectly fine, and this will always be able to switch them for you. Of course, not exactly the same.
What this illustrates is that when you're working with a class hierarchy like Scala Z that expresses these monadic constructs natively, you don't have to have the one-off implementation for each combination of types. You can create a very general expression of the idea. However, like if you want to stay within the standard library, like the previous slide, the definitions that we offered provide a really convenient way to do this, to express the same idea. So do check out Cascade.
Yeah, it's under development, but you know there are some gems in there that are useful. Okay, so we've talked about try, we've talked about option. I think probably the most next popular type that we use would have to be future. It's very difficult to model. And so I'd like to give an example of some of the quirks that you might deal with when dealing with futures. Presuming you have some functions that return futures, one of them waits 5 seconds and then prints slow cats. One of them waits just 1 second and then prints fast dogs. At some point in the future. Actually, on success is not required to happen immediately. And in fact, it takes its own execution context. So it's not necessarily going to happen right away, but it should eventually happen. And you know, in our examples, it will happen immediately. Just thought it's worth pointing out because the semantics of it are a little tricky. So if we're using a four-yield comprehension with futures, actually you will see slow cats print first, then fast dogs, because once it's in a four-yield comprehension, we don't know if we might end up using this piece of data later in the future. Future's a wrong word, but later down in the four-yield comprehension. However, if we instantiate this future, it's important to realize that it starts executing immediately. Even though slow cats is still first in the four-yield comprehension, because my dogs has already been started running, we see fast dogs print and then slow cats. I think it's just worthwhile to note that. The reason for that is because virtually every operation on future takes an execution context. So you can't, you can't like unwrap a future. You can't force it to complete. You have to simply wait, or await with a timeout, something like that. And very similarly to try, futures are actually based on the way that try uses NonFatal. So futures will actually catch NonFatal exceptions, and they say throwable in the failure case, but we know what that really means. Many of the functions that you might want on future are not necessarily already defined for you. We had the desire to get the first future that succeeded, or just one of the failures here. So you can actually use the find, just say, the find is defined as just give me the first one that matches this. But then it actually has a weird type signature because it always returns a success, even if everything was a failure. And then it returns a none in that case because it found nothing, which I find to be a little confusing. But you can implement it from this, and you can also implement it in other ways. You can look at the find function yourself, method yourself, and see how to do it. But there aren't as many primitive operations as you might like. So the Scala Z response to this is something called task. It's a little bit better behaved, I suppose. Only apply and fork actually take execution contexts. Otherwise, they reuse the same thread that they were previously using. And as you can see, when I defined hello, hello world didn't print. It was only when you attempt running it. So you have to build up this task, and then at the end of the world, you try and run it. And because it's using Scala Z, you get disjunction. And this funny type here is saying that this is a success, because the little dash is on the right and not on the left. If the little dash is on the left, that means failure. Great stuff. And so actually one of the points of the fact that task doesn't take execution context everywhere, you actually get, the idea is that you get much better thread reuse, and you don't have to have as many thread pool submit cycles. You get it easily. So if you use future with a lot of map and flat maps like we have in the past, you will see significant slowdown, and that is something to be concerned about. You can also lift things very simply into a task, and tasks also have many features defined for you. You can gather them unordered, and you just have a list. I actually took this example from Scala Z task, the missing documentation website, which I highly recommend if you ever want to work with tasks, because Scala Z documentation is a little lacking. But it's a basically equivalent form of future. All right, and finally, I'd like to talk a little bit about co-contra and invariance, because you've seen throughout that for the most part, Scala Z only uses invariant types, while Scala typically uses covariant. This gives you the nice property that if something requests a list of animals and you give it a list of bears, everything's great. But because of the nature of covariance, you actually have an issue here. You can't say it contains element A. This will not type check if you try and say it contains A. Because once you have a sequence of A that's covariant, and this contains is defined on this sequence, this makes the element into contravariant position. So this funny symbol, greater than colon, expresses the lower bounds. So unfortunately, what this means in the end is that contains is basically not type checked at all. It's pretty unfortunate in my personal opinion. The other thing is that other things that are in contravariant position, like adding lists together, if you wanted a list of any from this, that should be a type error. I don't think that's appropriate. It seems like not a good situation to be in. So that's why Scala Z provides iList and other types like that. iVector, I believe, is another one. So there's actually a plugin maybe you've heard of. It's actually, I think, in your bag that you got. There's a pamphlet for it that tries and helps with finding cases where equals doesn't equal and it's not type safe. Same thing with contains. Same thing with a lot of the things defined on sequence. Index of, less index of, or else. All of these things are in contravariant position. The parameters are. So you lose a lot of type safety. Actually, got this from Stack Overflow, but it works really great. You just stop using contains, right? You have a implicit class that allows you to define a method that's in the invariance type. And from this, we can now be sure that we have not made a catastrophic type error. I've written contains wrong, and it's passed the type checker. It's not pretty. So it's a hassle because you have to, again, it's all on you to define all of these things, right? But you can do it in your code base, and I think it's worth it for the type safety. Okay, I went a little fast, but we should all try and use the best tools available to us. I'm sure that's all why we're using Scala here today. And better ones will come along, but we can also fix up the ones that we have now to provide the best working environment possible. And if you have any questions, I'll be happy to answer them. You can go to the mics. No? All right. Well, this is the first talk I've given, so, great on the curve. And thanks so much for coming.